Okay, so in this video lecture, we're covering Chapter 15, Section 8, which talks about finding equilibrium concentrations. And this, again, is an icebox type problem. Remember, with icebox, you're given initial, you're given equilibrium, you're given K. And of those three values, you'll be given to and solve for the third. So on exam 1, I said we'd be given initial and equilibrium. We solve for K. Section 8, you're given initial and K, and you're solving for equilibrium. So that's what that section covers. And a note on the iceboxes in the chapter, section 15.8, there's several worked examples. The iceboxes are exactly the same as the iceboxes we'll be using in this presentation. So we're going to start with practice exercise 11. And again, we're given an equilibrium reaction. We're given our K value at 500 K, so the temperature. A gas cylinder at 500 K is charged with PCl5. And again, remember, charged just means filled. At an initial pressure of 1.66 atm. What are the equilibrium pressures of the three gases at this temperature? So why is this an icebox problem? You're given an initial value, you're given a K value, and you're asked to find E. So we're going to go over this together. Okay, so just on this next slide, again, I wrote down the initial pressure, the K value, and what we're asked to find. So icebox number 1, write down your reaction. So PCl5 gas in equilibrium with PCl3 gas and Cl2 gas, and your K expression. So the partial pressure of PCl3 times the partial pressure of Cl2, right, products multiplied, divided by the reactant, and then your icebox. So initial, change, equilibrium, and I have a column for my reactant, and 2 columns for my product. So initial, you put in the values that you're given initially. The only thing we're told about our initial value is that the partial pressure of PCl5, our reactant, is 1.66 atm. So we put that in there. The products are not mentioned. That means they're both 0. Again, our change, minus X for the reactants, plus X for the products. So just like we learned last week, all of my X's have coefficients of 1 because my balanced chemical equation, it's a 1-to-1 mole ratio. At equilibrium, I plus C equals E. So there we go. We added up 1.66 minus X, X, and X. And again, there are several worked examples in Chapter 15, Section 8. The iceboxes are the same as in my lecture, so go through those practice problems. And now step 3, again, think, how do I solve for X? So last week we solved for X because we were given an equilibrium value. This week we're not given an equilibrium value, that's what we're trying to find, but we are given a numerical value of K. So that's what we can use. Remember, K is products over reactants. So using our equilibrium row, my products are both X, my reactant 1.66 minus X. Plugging in the given value of K, right, K is 0.497 equals X times X over 1.66X. And what do we have? One equation, one unknown. We can solve this problem. Okay, so now algebra. X times X is X squared. Multiply both sides by 1.66 minus X, brings it over here. Now I'm going to distribute 0.497 times 1.66, 0.497 times X, and I end up with 0.825 minus 0.497X equals X squared. And you might notice this is now in the form, or getting towards the form of the quadratic equation that we can use. So to use the quadratic equation, I have every 0 equals X squared plus 497X minus 0.0825. So all I did, I subtracted 0.825 from both sides, I added 0.497X from both sides, and as you remember from your math classes, we can use the quadratic formula to solve for X. So I'm going to briefly show you how to do this. However, this is something you learn in math classes. I posted a video to a Khan Academy, or a link to a Khan Academy video that shows how to solve the quadratic equation. or use the quadratic formula to solve the quadratic equation. So if you want a refresher, please do watch that video. So with this form, I know my equation ax squared plus bx plus c, a is 1, b is 0.497, c is negative 0.825. So you'll plug that into your quadratic formula. And again, because we're using the quadratic formula, we get two values of x. X can either equal negative 1.19 or x can equal 0.693. So at this point, pause the video, use the quadratic formula to solve for x. Make sure you can get the same numbers that I do. Watch the Khan Academy video that's on Canvas as a reminder or a review for how to solve the quadratic formula, use the quadratic formula, and then play again. Okay, thank you for pausing the video. I trust you are all able to solve for x negative 1.19 or 0.693. Again, you get two solutions. And now it's our job as chemists to use rational thinking, which value of x is correct. To do that, we look back at our icebox. So in my icebox, I see x represents the partial pressure of PCl3 and it represents the partial pressure of Cl2. So does it make sense to have a negative partial pressure? No, not at all. Does a partial pressure of 0.693 seem appropriate? Yes. It's appropriate because it's a positive number. Right? You can never have negative values for a partial pressure. So that right away makes this first number wrong. So it's positive. That works for these values. Also, it's less than 1.66. So when I subtract x from 1.66, my equilibrium value for PCl5 will indeed be positive. So that's another thing to think about. Okay, now we've solved for x, we need to go back to solve the problem. The problem is asking us to calculate equilibrium partial pressures of all gases. So we use our equilibrium row. I know my partial pressure of PCl5 is 1.66 minus x. So that's 1.66 minus 0.693, which gives me a partial pressure at equilibrium for PCl5 of 0.967 atmospheres, ATM. Next, we need our partial pressure of PCl3, which is x. So that's 0.693. And lastly, our partial pressure of Cl2, there should be a P right there. Partial pressure of Cl2 is also x. So that's 0.693, and these are atmospheres. So all of these have units of atmospheres, which are the units that were given to start. And that's how we solve the problem. Again, quick review. We're given an initial amount. We're given a K value. We're asked to solve for equilibrium. I know it's an icebox problem because, again, initial, equilibrium, K. You're given to solve the third. I teach iceboxes in a way where you'll be setting up the icebox the same for every single section of the next 3 chapters. This is the same way that the textbook does for section 15.8. Write your reaction, write your K expression, plug in your initial numbers that are given in the problem. If a value is not given, that's telling you that it is 0. Change minus x for the reactants, plus x for the products, carry down the coefficients. 1 to 1 to 1, that's why all of our x's are 1. Equilibrium, I plus C equals E. So 1.66 atmospheres minus x, and x. Step 3, how do we solve for x? In this case, we are given K. K is products of our reactants. We're using the values from E in our icebox. We're given the value of K. And again, what we have here, one equation, one unknown. We can solve this problem using the quadratic formula. We get two values for x. Remember, x is your partial pressure of the products at equilibrium, cannot be negative. 0.693 works because that will give you a positive value for PCl5 at equilibrium. So lastly, to solve for the equilibrium partial pressures, we again use this E row. Partial pressure of PCl5, 1.66 minus x, which gives us 0.967. PCl3 and Cl2 are both x, so they're both 0.693 atmospheres. Okay, and that is essentially all of Section 8. Section 8 just covers many examples. So to get more practice, in your textbook, so page, you can read page 693 to 695. There are 2 worked examples, 15.9, 15.10. Work through both of those. Actually, pen and paper, solve them, looking at the notes as a reference. And then for more practice, 15.9 and 15.10 on page 697. That will help you out. And then you see example 15.11. You can look at that also. On page 699, simplifying approximations and working equilibrium problems. We will be covering that at the start of chapter 16, so you can skip over that. And then you'll read section 15.9, Le Chatelier, and that will be the next video lecture.